we can start the implementation details of Bing for the streaming system, making the jump from batch to streaming and Bing streaming primitives. Again, I'm Yi, I'm from Google. And before we begin, this talk goes into the specific Bing primitives for streaming pipeline and how they are used. If you want explanations as to why you would want and need these primitives and the general concept, you should go back to the first talk, making the jump from batch streaming motivation concept before jumping to this content. Firstly, for the streaming pipeline, we have a source and we have some processing stage and we write to some sink. And we start from the source. How do we read the data from the streaming source? This is the implementation details of Bing's I/O connector, unbounded I/O connectors to read from the source. Usually, you do not need to write your own connector. You use Bing's provided I/O connector to read from source like Kafka or other message systems. But it's good to know something about it because the source is where the event timestamp and the watermark is assigned to the system. So the Beam currently the modern way to read from source is to use the splittable dual funds. And the splittable dual funds is a p-transform that provides information to the runner about how much work there is to do and how much work already been done. So the runner can dynamically split the workloads. So to do so, the splittable dual fund requires a restriction tracker that tracks the client part of the work used to distribute and split works. For example, if you read from some message system and it has an offset that is monotonically increasing, the restriction tracker can track the offset that is already read and the offset has not yet been read. And it can claim a chunk of offset and to assign to the dual fund and then read within that chunk. And there is also a watermark estimator. It estimates based on the timestamp of output record or manual modifications. We can manually assign the approximate the current watermark. That is the earliest data that have not yet arrived. So this will allow for work to be rebalanced on the fly based on the long-running work items and allow for the auto-scaling of the system. And start with this in mind, the splittable dual fund are extremely important for I/O connectors and specifically streaming I/O connectors. Some of the heavily used Bing I/O connectors use the splittable dual fund implementation in Java. The Kafka I/O has two implementation. One is splittable dual fund and another is unbounded source. We'll go to that later. And the splittable dual fund implementation, the splittable dual fund is read from Kafka dual fund. It's an example of splittable dual fund used in the IO connectors read. And in Python, there is an example transform periodic impulse also based on the splittable dual fund. And this is used in some like generate a periodic and slowly input. Then you can pour some other source periodically. For example, watch for the file change, something like that. And further reading is the last in 2022 being submitted. There was a workshop dedicated to the splittable dual fund in Python, and the link for the example code is here. And another way to read from the unbounded source is called unbounded source. Bing have in Bing Java there are two type of source, bounded source and unbounded source. And this is the legacy way reading from unbounded source, and it's Java only. In Python we only have splittable dual fund API. And the unbounded source, I'm still talking about it because it's still heavily used. And there is a new IO connector in the latest Bing. I think it's 2.57. Solace IO, I read from Solace message system, is based on this unbounded source. And actually, internally, unbounded source is executed by a splittable Dufang writer. But before the splittable Dufang existed, this was the way to read from unbounded source in Bing. And it's a read. It uses a read transform as a source node on the of the job graph. And the unbounded source has a method create a reader. It creates a reader that a runner use to read data from source. And the reader has two basic methods, start and advance, to conduct the actual read. And the runner then gets the current element handled by the reader by the get current method. Arguably, this is an easier way to read from money source. The API arguably is easier and more straightforward. That could be why it's still popular. So it's much less versatile than the splittable Dufang because it has to be a source node of job graph. And we essentially it's not convenient, if possible, to load balancing it. So it actually now executed via a wrap of splittable Dufang on the portable runners. And some example of Bing IO using unbounded source, the JMS IO, Solace IO, and also Kafka IO has a unbounded source mode. So in both cases, the source tracks some metrics and also for the system. The most important one is the watermark, the earliest data that the approximated earliest data in event that are not yet received by the system. Remember that we must lean on heuristics to estimate the watermark and can never be perfect, that I explained in the previous talk. And optionally, there are some other metrics that help runner to do the scaling decision. First one is get backlog bytes. If it can query for the source to check how many backlogs is yet to receive. If we want the latency to be as small as possible, we want the backlog to be small. Otherwise, we process very old data, and this is the source of latency. So if the backlog of bytes is large, then Bing can suggest the runner can act on this situation and ramp up the more workers. On the other hand, the source can report a throttling matrix. This is by using matrix counter with dedicated name. This functionality existed in Bing, not complete, and in incoming next release, this is going to be a more complete functionality. That is, the source or any Dufang can report a throttling matrix, and the runner can act on this and get a back pressure and try to scale down if there are too many time wasted on the throttling. So the source tracks the watermark and also some metrics that to help runner for the scaling decision. So the next part of the pipeline after the source is the processing stage. We usually have some user Dufangs and accept elements, incoming elements to processing. And the element means any data and like incoming Kafka message or something like that. And for each element, there are some so-called metadata associated with this element. It's not necessary to metadata. For example, the most important one is the key. Is also part of the data. But the Bing and the pipeline will use this metadata or and the key to decide how to process it, how to group it, and how to materialize, when to materialize it. The most important one is the key. We already mentioned this data processing system Bing. If we trace all the way to the 2000, it can be originated from a MapReduce, and essentially the primitive way to do is to materialize the keyed data, very large amount of keyed data. So the data of the same key will be processed in the same worker and materialized together. So key is the most important one, personally, I think, in the streaming system. And also the timestamp. The timestamp of the data is the event timestamp. And we have a windowing. do spatial part do a spatial p-transform that window this data into some window. We'll talk about a specific window later. And after the window into transform applied, each element is assigned to a window. And note that an element can be associated with multiple windows, like in the case of slicing window, for example. And after the group by key or anything that materialize the window and firing the window, and each element will have a pen that it tracks on which time the window is filed. Every pen is implicitly associated with the window, that's it. So we first talk about the window strategies. In Bing, there are three types of window mostly. Of course, you can define your customized window. And the provided window, three types. The first one is global window, is a default. If you do not use window into p-transform, all the element is in global window. It's a large single window from Unix time 0 to max Unix time. And by default, Bing operates on the global window until told otherwise. And the second is interval window. There are two types of them: fixed window, fixed interval window, sliding window. We'll show them later. And lastly, the session windows. The fixed interval window, you can apply it in this way. Then each element, timestamped element, will be assigned to a single window that is within this time. And there is no gap in windows and also no overlap between windows. On the other hand, the sliding windows has overlap between them. And the sliding window then has two basic parameters. One is the duration and another is the interval. Each window has a duration, and between two windows, the interval is not the same as the duration, is essentially smaller than duration. We can also see the fixed window as a special case of sliding window with the same duration and interval. The effect is a series of windows with some amount of overlap. So the data can exist in multiple windows. For example, if the data, the event time is here, then belongs both window 0 and window 1. Okay, the use case of fixed windows is, for example, we want to store our incoming data. Each hour we store it in some file. Then we window them into some fixed window and call the write transform. And then it will write the data within the same window to the same destination and a different window into different destination. We then store our data divided by incoming timestamp by the certain interval. And a use case in the sliding window is if we want to do some offset average, like a 30-day average of stock price, something like that. And we'll have each day we have one average, right? And it's the 30 days before, and the second day is 30 days before. They have overlap. This kind of average is ideally be treated by the sliding windows. And finally, the session window is a dynamic windowing. It's essentially based on key. So window events that occur with a length of time shorter than some timeout. This is merging windows as they can grow and merge with some other windows as data is processed. So we have some data and belongs to this window if there is no such data between the minimum gap, then this data belongs in two different windows. But if we have a data with the same key that arrives earlier than the assigned minimum gap duration, they all belong to the same window. This is pretty much like a session. The session has an expire time. And this session window is useful to track some discrete event, be the event, but we want to group this event into sessions if they occur frequent enough. So After windows, then there are triggers when we materialize then or group by key, use group by key and decide when to file those windows. What is a trigger? Trigger are a mechanism that declare when output for a given window should be materialized relative to an external signal. Triggers can also be configured to file multiple times and allow for the output for a window to be updated over time as more data comes in. This is how Bing can handle revision to data or data that comes in late. And for each time a window filed, a window triggered, a pan is assigned. And the pan is pretty much integer and is increasing tracking the current materialized data belongs to which pan. When a trigger is activated, the materialized output for a given window is commonly referred as a plan. That is the more formal definition. Multiple pans can be output for a single window as processing continues. Well, trigger system arguably is one of the most confusing concepts in Bing. It's harder to handle correctly, so one needs to be careful, and one can also implement some custom trigger also. So the common types of trigger, first one is repeated update trigger. The output for a window can be repeatedly updated, either with the presence of new records or after some amount of processing time. Using this trigger generally requires some balance of latency and cost, depending on how expensive the transform being calculated. And the second type is completeness triggers. And when the system thinks the output can be materialized, and then it will file and trigger. This allows for handle the late missing data. And we'll have some example. This is how the completeness trigger can be written in Bing Java SDK. We have some p collection of string items, and during a window, we use a fixed window of 1 minute duration, and also define how it triggers. This use a repeatedly trigger, and after the watermark past the end of window, and it discards the failed plans, which we will come to later. There are two types of accumulation mode, and this is a completeness trigger. When the watermark already passed the end of window, we trigger it. And the second one, the repeated trigger, we do not use we can use a global window instead of a fixed window. So all the data belongs to the same window. If you do not have a trigger, or if we use this one, it will no longer fail. And actually, I think it will generate an error if you write global window with this trigger. The BSDK will remind you this is wrong. If we use global windows with a repeated trigger, and after pan element count at least 5, which means if we should receive at least 5 elements, then we trigger the file and send the data downstream. And how to manage pans? We just mentioned before here. You see this discarding failed pans. When you specify a trigger, you must also specify a accumulation model for the window. And what do we do with data in pans that have been emitted before? The accumulation mode is demonstrated below. Basically, an accumulating trigger re-emits the data that was previously emitted along with the new data. It depends on your use case, right? If your streaming pipeline, like doing some combine from some live data, and the data can arrive early or arrive late, and if it arrives late, we want to revise the data with the new incoming data, then we want to choose this accumulating filed pans. Each time it triggers, it emits all the data within this window, so we can do a live revision as the window triggers. And another accumulation mode is the discarding filed pans. That it was the example I used before. This is when you use the trigger as a form to materialize or to divide the data. For example, divided by every at least 5 elements. Then you already materialized and processed the first pan. And on the second pan, you do not need the information from the first pan. Then you can use the discarding filed pans. This talk is mostly taken from this book, and also we can refer to if you want to learn these Beam primitives in an interactive way. You can check out the Beam programming guide, which has a detailed discussion for this concept. Yeah, and thank you. We have a pipeline that demo the windows. So now let us create some data. We'll use some like simple data. That is just the time year of 2021, the full moon. There is actually 13 of them. The timestamp of each full moon. And we run this pipeline actually. Our data is a tuple at the first. The first element of the tuple is the timestamp, and the second is the name of this full moon event. And we have astronomer event transform that first create this data and then use the timestamp value, convert this tuple into a timestamp value. This is basically how the timestamp is labeled associated with each data. With this transform, if we print these values, we only see the value part of the data. We do not see the timestamp. It's not because they are gone, it's because this becomes a metadata or timestamp for each element. If we just print the element, we don't see the timestamp, but it's still associated with the element itself, and the windowing will react on these timestamps. We'll show it later. So we first demo the global window. So all pipeline use global window as default. This is the single window that covers entire option. In many cases, especially in batch pipeline, this is what we want since we want to analyze the data that we have. This is a pipeline we have, and this will print the global window. This print window info will print the window and the timestamp and the element. Now all the data is in the global window. And if you checked out the Colab, I can also paste it here. There is a demonstration for the global window. And you will see all the elements belong to the same global window. This is just a visual demonstration of this print window info. Then the fixed time windows. If we want to analyze our data like hourly, daily, monthly, we might want to create event evenly spaced intervals. That's when we use fixed time window. So this pipeline then first will window the incoming elements into fixed windows, which the fixed size and of 3 months per window. That is a quarter. And you will show the window of each element. Here is the January 3rd to April 3rd belong to the same window. And also some element belong to second window, third window, and fourth window. It shows the first has 1 element. Oh, so this is some new moon and full moon astronomy events. not all the formats, sorry. But anyways, this also demonstrate the window size and the element. We can see the elements are distributed into the fixed windows, and each window has the same window size. And then we check the case of session of the sliding windows. Let me also paste the sliding window. Maybe we want to fix that window. We don't want to wait until window finish, so we can start a new one. Then this is a use case we use sliding window. It's very similar in implementation. It's very similar to fixed window. You also have a window into, and don't use fixed window, just use slide window. The node has two parameters instead of one: window size and window period. Then we print this window. It looks much longer because now each element can belong to multiple windows. For example, this March equinox, it belongs to 3 windows, and starting from January, February, and March, and each lasts a quarter. And for the visual demonstration, also had it in the Colab. I pasted here, and you'll see the element and the window. The window is a sliding window, and each element, it belongs to multiple windows. Here, the first one belongs to 3 windows, and the second one belongs to actually also 3. Nope. And finally, the session windows. I pasted the description here. Maybe we don't want to regulate regular window, but instead we have the window reflect the period of where activity happened. Session allows us to create those kind of windows. We know how to specify a gap size in seconds, which is the maximum number of seconds of inactivity to close a session window. So similarly, I have the code below and I execute it. So now the window into have sessions, and the session only has one parameter, that is gap size. When the same element, we'll see how it goes. I also paste the demonstration here. And essentially the elements are grouped into these sessions, and each session can have single element if within the period of gap size it does not see another one, then this window just ends. And then here we have this element, and we still see in upcoming elements that has timestamp smaller than the gap size, then these elements are in the same windows. And this is how the session window works. So this is a basic demonstration. And now we go to another one. That is a real use case. This streaming taxi rider, which is a very good example to demonstrate the windows. So again, I use this Dataflow notebook, and if you are not within a GCP environment, you will first need some Google Cloud CLI, some command line tool, and to interact with the public PubSub resource. So we first import something, set up the pipelines, and this IB is interactive runner. So being Python SDK provides an interactive runner that makes it convenient to use in a notebook environment. And we create a pipeline that run with the interactive runner and read the data from PubSub. This is just we define the pipeline. and get a P collection. We haven't run the pipeline yet. And if we use this interactive runner, we can show the data in real time. We'll see here. To use it very simple, just use interactive runner show, and it will you'll see the entries are increasing because this is a streaming source, and the incoming streaming data never ends. And basically, this is what the data looks like. It's a row and has a schema like this: a rider ID and some pointer, the latitude, the longitude, and importantly, there is a timestamp associated with each element, and there is a meter reading for this ride. And this is some real-time data. And what we do first is group this data into a window using a sliding window of, I think it's 10-second duration and 1 second interval between each slide. And we'll see how it goes. We can okay. This we can show the live data after we put them into Windows. And no, it prints a window. First, we'll see the pan is still pan 0 because we have not yet filed it. We do not use a group by key or something. So it's not filed yet. All the pan is pan 0 yet. And we can see it divided into some windows. It's not obvious here, but it's more obvious here. And each color is one window and is in some slided manner. And some graph. If you are interested, you can go this into more detail. And I just do an overview. And then we do some processing. That is, we first extract the one field called a meter increment from our data, and then summed all element by window. Use this combine globally sum that will sum the element within the same window. And now we show the result. And it now propagates as we run the pipeline because it's a streaming pipeline. Alternatively, or in production, we always write it to something instead of just show it in the notebook. And we can also use write to PubSub. Yeah, this is a basic use case of the streaming pipeline with window. Yeah, thanks. That's the end of the demo.